So far in the past 2 weeks, we have discussed electrostatics, where we learnt how to calculate the electric field for given charge densities and boundary conditions. Now, we are going to switch from this week onwards to learn about magnetostatics. So, to begin with, a magnetic field is identified by the force it applies on moving charges. Known as the Lorentz force, which is F equals Q V cross B. So, unless a charge is moving, magnetic field will not apply a force. So, that is how you identify a magnetic field, and it comes from arises from currents, or equivalently you can say moving charges, all right. So, this is what we now need to formulate. Furthermore, the calculation of magnetic field and we will later define a related potential, which in this case would be a vector potential. So, this calculation is more complicated than that of an electric field. Why? Because it involves cross products rather than dot products. So, let us write that also. It involves cross products rather than dot product that we saw in the case of electrostatics. Furthermore, instead of divergence of a vector field, in case of magnetostatics, here we deal with curl of a vector field, and that also makes it a little more complicated. So, you are urged to brush up your vectors and vector calculus. Of course, as I go along, I'll guide you through the whole thing. So, to begin with, the counterpart of Coulomb's law in magnetostatics is Biot-Savart law. And I wish to emphasize at this point that Biot-Savart law gives magnetic field for a steady current. What does steady current mean? That there is no time dependence in the current. What that means is, if we take a current density J r, then del dot J is 0. In case this is time dependent, right? In case the current density has time dependence, in that case I have divergence of J plus d charge density change equals 0, which is known as the continuity equation. So, we are dealing with time independent or steady current. So, we are dealing with steady current. So, for steady current, suppose I have a loop in which this current is flowing. Let me make a coordinate system, origin. From the origin, take a small section of this loop dl prime, and I want to calculate the field at some other point r. Connect a line from here to here, then magnetic field at r is given as mu naught I over 4 pi integration dl prime cross r minus r prime over r minus r prime cubed. So, notice, as I said earlier, now we are dealing with a cross product. All right, let me write this clearly in the next slide. So, given a loop, some loop where a current I is flowing, going around the complete loop, B at some point r is given by integrating over the loop. Take a small section at r prime. This distance is r minus r prime. Then I have B at r is equal to mu naught I over r minus, sorry, I will write it again. We have B at r equals mu naught I over 4 pi, and then I integrate over this loop, which is a line integral, this cross product L prime cross r minus r prime over r minus r prime cubed. You can see, like Coulomb's law, the dependence of B is 1 over distance square. So, this is how you calculate it. Now, let us do some examples of applying this law. The easiest one is a loop in the xy plane, a circular current loop in the xy plane, has radius r, and I want to find the field at a height z from this. You must have done this problem in your BSc and MSc, but I now want to use the full mathematics machinery so that you get used to it. This is in the x y plane, the radius is r, and it is carrying a current I. So, let us see, I am calculating the field at r equals at point z on the z axis. The current I is in the xy plane. So, dl prime is going to be along the loop, the radius d phi in the phi direction, and in fact, I should write this as prime. R is the radius. I could also write this as equal to, so dl prime, if I were to write this in the Cartesian coordinates, is also going to be equal to dx in the, it's in the phi direction. So, I can write this as dx, let us see, in the okay. One second here. So, I can write this as r d phi prime. Phi prime is nothing but minus sine phi prime x plus cosine phi y. This could be written as minus r sine phi prime is nothing but y. So, I can write this as y x plus x y d phi prime. I could also write this as r cosine phi prime in the x direction, d of this, plus d of r sine phi in the y direction, which would then come out to be dx x prime dy prime y. Notice that x and y unit vectors are fixed, so there is no prime on that, whereas when I am writing phi unit vector, there is a phi prime. It is easiest to do this calculation in cylindrical coordinates, because you see the expression for dl prime here that I have written is easiest in cylindrical coordinates. So, let us do that calculation. So, I have this ring in the xy plane. I am calculating field at z. So, I have r equals z z, dl prime is r d phi prime in the phi prime direction. So, I have b r equals z z equals mu naught I over 4 pi d L prime, which is r d phi prime unit vector cross r minus r prime. So, that is going to be z minus s prime unit vector. That is where the position is at some s prime, and s prime in this case happens to be r, because current is at r, divided by z minus r s prime raised to mod of this raised to 3. So, this will come out to be mu naught I over 4 pi, and there will be an integral over 0 to 2 pi. R will come out, integration d phi prime. When I put this over the circle, it means I am doing the r integration over of phi prime integral over 0 to 2 pi d phi prime. Then I have phi prime cross z. Phi prime cross z is minus s. So, I can write this as z s prime with a minus sign, and phi prime cross s is minus z. So, this will become plus r z divided by z square plus r square raised to 3 by 2. So, let us write this neatly. When you write this neatly, you get B at z is equal to mu naught I r over 4 pi integration 0 to 2 pi d phi prime minus z s prime plus r. There is something wrong that I am getting 2 r I had already taken care of. Had I? Let us see. So, I get z s prime, and here I get, yeah. So, this z will not be there, it is only z vector, z over r square plus z square raised to 3 by 2. And that is simple enough, because this part is no phi prime dependence, and therefore, I get mu naught I r square over 2 over r square plus z square raised to 3 by 2 in the z direction. What happened to the s prime term? That is, s prime term is equal to minus, sorry, s prime term is equal to cosine phi prime x plus sin phi prime y, and integration of z s prime d phi term is therefore equal to 0. So, the field comes out to be in the direction of z, and its magnitude is this. So, this is a straight calculation. I am not taking, I mean, you are probably used to doing this calculation by taking a little thing out here, calculating the component and adding it up. I have just done this in one integral. That is it. And that is example number 1. Let us do example number 2. In this example, suppose I have a strip, thin strip, infinitesimal width, carrying a current K in the y direction. The strip is in the xy plane from minus infinity to plus infinity, and in the x direction it extends from minus a by 2 to a by 2 in the x direction. K is a unit, is a vector quantity. This is surface current. So, this is defined as current per unit length. This is defined as current per unit length. So, I want to calculate the field due to this strip, field due to this long strip on the z axis. Now, here is best to use Cartesian coordinates. So, we will be using because of the symmetry. So, again when I calculate B at some point z unit vector, this is going to be at, we have mu naught I over 4 pi integral d l prime r minus r prime over r minus r prime cubed. However, in this case I do not have an I, right. In this case I have a surface current. So, we have to build up the current from the surface current. We will do it formally later, but right now let us see how do we do that. So, let us again make this strip. This is the z axis, x, y, z. I will take a small strip at some point x prime, y prime, length dy prime, width dx prime. Then I can write the current in this as k dx prime and going in y direction. This is the current, and therefore, I can, and dl prime is equal to dy prime in the y direction. And therefore, I can write let me just make the whole picture again, because we have come to the new slide. I have taken a small strip here, dl prime equals dy prime y, current di is equal to k dx prime, and let me see if I used a vector there also. Yeah, so current I used a y vector and I used a y vector in dl prime, but that does not really matter. because I have to take this vector only at one point, right. So, I am writing as a scalar quantity, and therefore, B is going to be at z unit vector is going to be mu naught over 4 pi. Now, current, small current is k d x prime, and x prime extends from minus a by 2 to a by 2. d y prime is another integral. Y prime varies from minus infinity to plus infinity. Y cross r is at z z minus r prime is at x prime x minus y prime y divided by this whole thing cube. So, that is going to be x prime square plus y prime square plus z square raised to 3 by 2. That is going to be your answer. So, let us see what does it come out to be. So, B z comes out to be mu naught, k is a constant, so can be taken out, over 4 pi integration minus a by 2 to a by 2 d x prime minus infinity to infinity d y prime. Y cross z is x. So, therefore, I can write the top as z x, y cross x is minus z. So, I can write this as plus x prime z, and last term is 0 divided by x prime square plus y prime square plus z square raised to 3 by 2. That is as simple as that. Now, for the second term, for the term x prime z divided by whatever, integration minus a by 2 to a by 2 d x prime will give 0, because this is an odd integrand, and therefore, B z z is equal to mu naught k over 4 pi integration minus a by 2 to a by 2 d x prime minus infinity to infinity d y prime, z is there, divided by x prime square plus y prime square plus z square raised to 3 by 2. Again, you can do this integral by substitution, and I will leave that for you, and you get B z z is equal to mu naught k over pi z over modulus z tan inverse a over 2 mod z in the z direction. That is the answer. For you, I am leaving this, perform the integral, and I am also leaving for you check various limits of this answer. What are the various limits? A tending to infinity, so then it becomes a whole sheet, z tending to 0, and so on. So, I will leave that for you. As the third example, and this is from Jackson's book. It says starting with the expression B equals mu naught I over 4 pi integration dl prime cross r minus r prime over r minus r prime cubed at point P at R show that field by loop that carries current I is B equals mu naught I over 4 pi gradient of omega, where omega is the solid angle formed by the loop at P, and omega is positive if vector from P to the loop surface is such that n dot at vector is greater than 0 and negative otherwise. So, let me explain this problem, what this person wants. What is asked is that you have a loop, current loop carrying current I, and I have a point P somewhere. Which is at R, and various points here are given by R prime, and here is this small element dl prime, so that the field is given by this expression that I have written earlier. Then this expression is related to the solid angle formed by this point P on this loop. So, let us make it like this. Now, this is a solid angle formed, this is a solid angle here, which is omega. In the case shown, the normal vector n is like this, given by the current flow. So, n direction is given by the right hand rule for the current flow direction. So, you can see in this case n is pointing out of the surface. In case the current was the other way, I am showing this with this green color, then the right hand rule would have given me n going in, n towards P, right. So, that is how the sign is decided. So, let us now solve this problem. So, we have been given this current carrying loop I, and I want to calculate the field at some point P by that Biot-Savart integration. So, that field B is given by mu naught I over 4 pi integration over the loop d l prime cross r minus r prime over r minus r prime cubed. Let us see what the vector r minus r prime is. The vector r minus r prime is this, pointing towards P, that is r minus r prime. And the vector going the other way would be r prime minus r therefore. So, how do we go about doing this? And this I want to show is equal to mu naught I over 4 pi gradient of omega. So, this is a nice problem that brings out all the vector complications, all the machinery of vector calculus into play. So, first I recognize that there is an integral over a loop, and whenever there is an integral over a loop, I have Stokes' theorem that says integration over a loop d l prime dot some vector v r prime is equal to curl of this vector, let us write this as r prime dot d s prime. Right. So, what it says is if I have a loop and I want to calculate the integral, line integral over the loop, right. Instead, I can do it an area integral over the loop by taking the curl of the vector. So, now I want to transform this somehow into this formula. For this, I would like you to recall the tricks used in solving problem 67, I think. I think it is problem not 67, let me check. This is problem 61 of chapter 1 of Griffiths. Recall, go back there, stop for some time and see what those tricks were, and then I am going to use the same tricks here. So, on this after this integral, integration d l prime cross r minus r prime over r minus r prime cubed using this theorem d l prime dot cross V r prime is equal to integration curl of V r prime dot d s prime. Since I want to bring a cross product, let us take using the tricks in that problem, take V r prime to be equal to some constant vector c cross r minus r prime over r minus r prime cubed. Do this where c is a constant vector, and therefore, the integral now becomes integral of d l prime dot c cross r minus r prime over r minus r prime cubed is equal to integral curl of C cross r minus r prime over r minus r prime cubed with respect to primed variable dot d s prime. Now, use the identity for curl of A cross B and also cyclic property of this product A dot B cross C. So that you can write this as C dot A cross B and so on. Use these, go around, you will find that I can reduce this integral to the left hand side would come out to be using all this integral of C dot r minus r prime over r minus r prime cubed cross d l prime. C comes out because it is a constant vector. So, this will be the left hand side, and the right hand side will come out to be minus C dot grad of omega, right hand side. You may wonder how I got this grad. So, you may be wondering how grad prime changed to grad. For this, along the way I use this. I said that grad of 1 over r minus r prime is equal to minus grad prime of 1 over r minus r prime was used. All right. So, this and higher order derivatives. So, once you get this, you can see easily that C is an arbitrary vector. Since C is an arbitrary constant vector, I can take this to be in the x direction, y direction, z direction. So, I can show it for all three components, and that immediately leads to, let us check what were the expressions, that immediately leads to integration dl prime cross r minus r prime over r minus r prime cubed equals grad of omega, and the answer follows. So, the tricks we were used were 1, use vector C cross r minus r prime over r minus r prime cubed in Stokes' theorem. 2, along the way del 1 over r minus r prime goes to minus grad prime 1 over r minus r prime, and for the derivatives involving r minus r prime. Third, which I did not say, but I am going to say now, is d omega for the surface is going to be ds prime dot r minus r prime over r minus r prime cubed, where ds prime. So let me explain the third one. If here is this surface, here is a small ds prime, and here is this point r. This vector is r minus r prime. Then this solid angle here, this is n, this is the direction of ds also, is going to be d omega is going to be minus r prime dot ds prime over r minus r prime cubed. This minus sign takes care of the fact of that n and the point to that ds prime is roughly along n, or that dot product is greater than 0. So that's how the sign also in the problem was decided. So I've used these to show how to solve this problem. So let me now summarize this lecture. We wrote Biot-Savart law for magnetic field produced by a steady current and applied Biot-Savart law to solve for B for some given current distributions. Thank you.